here we go. Hello everyone, my name is Dan the Tutor, and welcome to the Physics 202 Exam 2 review session for Spring 2025. I already did the intro off camera, so I'm just going to skip that part. And let's go into our first topic, which is RC circuits. So RC circuits, I believe I covered a little bit in the first exam review because we were unsure if that would be on that exam or not. It turned out that it was not on that exam. It's going to be on this one. So a lot of this will be review for the notes, but I made sure to include all new questions than what we had on the first exam review. So first with RC circuits, excuse me, this is going to be the setup. You see that it's got a battery and a resistor and a capacitor. And this switch right here is basically going between 2 points. So I know I didn't leave a lot of room here for you to write, but I'm going to write it here anyway. We have the charging position, which is going to be battery, resistor, capacitor, like that. This is charging. And then discharging, that's just going to be no battery anymore. We disconnected it. And now it's just the capacitor and the resistor. And the thing about discharging, from a conceptual standpoint, the capacitor acts like a battery until it dies out. It's like a temporary battery that dries out very quickly within a matter of seconds or milliseconds. So there's a bunch of things to know when it comes to charging versus discharging. Let's go into everything. So first we have voltage on the capacitor. That equation, which will probably be given on an equation sheet, is going to be VC equals V battery times 1 minus E to the negative T over tau. What's tau? Tau is known as the time constant. You really don't need to know what it means. Just know that it's equal to R times C, resistor times capacitor. Then we have voltage in the resistor. Voltage in the resistor is going to be VR equals V bat times just E to the negative T over tau. No 1 minus. You can also write this equation like this. V battery minus VC. That makes sense because it's the battery minus the voltage in the capacitor. It's literally like they have to add to the battery, so battery minus capacitor leaves you with resistor. Either one of these will work on the test, but usually not both. You know what I mean? Like it's usually one or the other. Well, that's technically not true. The reason I said that is because there was one year where you had to use this equation, and I've seen also questions where you just use that equation. So how do you know which one to use? Sometimes, well, first of all, you're going to have all the information. Like both of these, you'll have enough information to use both. But if it's multiple choice, which is the question I'm thinking about when the year it had to be that equation with Professor Young, it was in the answer choice. It looked more like this, and there was no E anywhere. So that's why I'm saying it was the right one. But of course, you already know in physics, there's multiple equations sometimes, and you just have to pick the right one based on the information you have. Then we have charge on the capacitor. Remember that charge, C equals Q over V. This is from exam 1. Well, if you just multiply both sides by V, and you remember that V is V battery times 1 minus E to the negative T over tau. That's the voltage in the capacitor. So that's the equation for charge on the capacitor. Then we have current in the circuit. Remember Ohm's law, V equals I times R? Well, you can divide both sides by R, but just remember, it's the voltage in the resistor divided by R. It's not the battery, it's not the capacitor, has to be the resistor for current. Why? Because that's the rule. And then the last two things we have are short time versus long time. This is when, oh, we got Kyle. This is where in the problem where it says short time, like the immediately after the circuit's been switched, and then long time is after it's been switched for a long period of time. So, for instance, with short time, you need to know that the capacitor is just a wire. And what that means is that there's no voltage, but we are at max current. So after a short time, the capacitor is a wire, which means that there's no voltage on the capacitor, and we have max current in the whole circuit because it's in series. Any questions so far? And then the last thing we have is long time. And the wording in the question would be after the switch has been closed for a long period of time or something along those lines. We say the capacitor we say is an open circuit. And what that means is the capacitor has all the voltage. The capacitor has all the voltage, but there's no current. Current 0. Any questions on any of that? Okay. Now we're going to go to discharging. Discharging, I'm going to go a tiny bit faster because a lot of this is the same. So first, voltage in the capacitor. Vc equals V bat times e to the negative t over tau. Yes, this is the same equation as the resistor for charging. Yes. It's just missing the 1 minus. Then we have voltage in the resistor. That's going to be Vc equals Vr. They're just equal to each other. Very simple. Charge on the capacitor is the exact same thing. Q equals capacitance times Vc. But remember, Vc is different now. Now it's e to the negative t over tau. Before it had the 1 minus. Current in the circuit is still VR divided by R. That's the same. Voltage in the resistor divided by resistance. And then after a short time, we say the capacitor acts like a battery. This is what I was saying earlier. And when that happens, it means it has all the voltage and we are at max current. And then finally, after a long time, we say the capacitor is a wire again. And this one's interesting because there's no voltage and there's no current. As far as we're concerned, it's a dead circuit. Nothing's going on. Any questions on any of that? Okay. Then we're going to move on to first problem of the night. You are designing an RC circuit to charge to 99% of the total voltage in a time of 3 seconds. The voltage source is 12 volts and the resistor is 250 ohms. What capacitance should you use to achieve this? So this is pretty straightforward. It's going to be the charging equation because it says right here, charge to 99%. So I know it's charging. I know the total voltage, V bat, it says 12 volts in the problem. Time is 3 seconds. Resistor R is 250 ohms. And we're trying to choose the capacitance. So we're solving for capacitance. So then what I'm going to write is Vc, voltage in the capacitor, equals V bat times 1 minus e to the negative t over tau. And I'm just going to plug in for tau, it's RC. I usually do that from the beginning. Now the hardest part of this problem comes up right now because we know V bat, it's 12. we know t time is 3. We know r is 250. And we don't know c. So the problem is I have two unknown variables, right? I don't know VC, and I don't know capacitor either. Any ideas on what I'm missing? That's right. It's 99% charged, like we said earlier. So what that means is I have to do 0.99 times 12. Simple as that. I did all the calculations earlier today. So that's going to, well, what's funny is I didn't even compute this because the 12s just cancel. So then 0.99 equals 1 minus e. I missed a negative sign here, sorry. It's negative 3 over 250c. And then the rest of this is just algebra. I subtract 1, that gets me negative 0.01 equals negative e to the 3 over 250c. I need to go on fresh paper because I'm out of room already. But we're at negative 0.01 equals negative e to the negative 3 over 250c. The negatives cancel, which is great. And a lot of people don't know what to do at this step because they failed Algebra 2 or in the very least forgot it. What do I do at this step to solve for c?
Take the natural log of both sides.
Correct. And if you didn't know that before, now you know. And the reason why this works is because ln and e cancel. So then natural log of 0.01 equals negative 3 over 250c. From here, I multiply both sides by c. If you want to multiply by 250c, you can, but you're going to divide the 250 in the next step anyway, so I'm not going to. And then the last step is divide both sides by natural log of 0.01. And that will look like this. You'll notice the ln 0.01 and the 250 share in the denominator. And we'll get a final answer of 0.0026 units are F farads. If they ask for millifarads times 1,000, 2.6 millifarads. And there we go. Any questions on that one? Anyone still writing? Okay. One final bonus question for you. At this moment in time, what's the voltage in the resistor? Well, you don't need any fancy formula. You just have to remember it's V battery minus VC. V bat was 12. VC was 12 times 0.99. You just plug this in a calculator. I did not do this because I just thought of this question now. But it's going to be 0.12 volts. Very small. That's if they asked for the the voltage in the resistor. That's how you do it. Any questions? Okay, excellent. Now we're going on to perhaps the most confusing topic of the night. It is nerve signals, which is also going to have resistivity in there, and I'll explain what that means in a minute. The reason why I say it's the weirdest topic is because I've been tutoring this class for a long time at many different colleges. Professor Young is the only one who teaches this out of anyone I've ever met. So for a while, just like you kids, I had to learn this too for the first time a couple years ago. But, you know, now he's leaving next semester, so I can then forget about this, which is great. So first, I guess I'll draw, well, I already have what the circuit looks like. And, you know, sometimes he puts a little, you know, cylinder on top of this, but this is essentially what the circuit looks like. That's all that matters. Will our equations change because now we have another resistor and this is now in parallel? The short answer is yes. Literally everything's going to change. The good news is I'll give you the shortcuts because we just need to know the shortcuts for the test. So before I give you the equation, I left a little space right here in this bottom left corner. I want you to write this. I want you to draw a cylinder that has like an outer layer around it, like this. And then I need to label some things for my equation. This distance is L, capital L. Lowercase d is the diameter of the cylinder. And then this little distance right there, that's going to be T, the thickness of the cylinder. All of the equations are going to use these three variables. So first, we have the resistance equation. This is just for a normal resistor, what I'm about to write. R equals rho L over A. That is not P, that is Greek letter rho. Yes, I know it looks like a curly P. If you want to draw a curly P, that's fine, but it is called Greek letter rho, like row, row, row your boat. Anyways, we know what L is already. Rho is resistivity. Rho is resistivity. It's just a constant. It depends on the material. Like, for instance, different metals have different resistivities. He's going to give it to you on the test, or it's going to cancel. It has to be one of two. Or you're solving for it. There's no circumstance where you have to know the resistivity of anything, so don't worry about that. Now, finally, this A is the cross-sectional area. Cross-sectional area. And don't worry, I'll be doing the thinking for that in the next two equations. So with axon resistance, just know that the nerve signal is made of an axon, which we see at the top in the circuit, and then a membrane, which is these two things in parallel. Does it matter that you know what that means? Honestly, no, it does not. What matters is that, and again, I'm assuming these equations will be given to you, but I'm going to write them down anyway. It is rho L over pi r squared, or rho L over pi 1/2 d squared, because it's 1/2 the diameter for radius. Any questions so far? And then for the membrane, our mem is equal to numerator rho t, denominator pi dl. And of course, I think this is obvious, but I'll write it anyway. Twice the radius equals the diameter, in case you didn't know. Now for this section in the bottom right, where we have this nice section right here, I'm going to tell you the shortcuts. The shortcuts are, you only need to know this circuit for a short time and a long time. Actually, I'm going to draw it on a new sheet of paper. I need more room. So we have short time, and then we're going to have long time, just like before. So after a short time, the capacitor is still a wire. That much is true. I am not going to say the stuff I had earlier, which was the voltage was 0 and we had max current, because it's very different, like I mentioned. But the capacitor is still a wire, which means the circuit is going to look like this. Oh, wait, I messed up. Sorry. There's no second resistor. It's just the top resistor. This resistor is gone. It got replaced by the capacitor, which again is just a normal wire. The proof for that involves combining resistors in parallel with a resistance of 0, and I'm not going to derive that, so just memorize this. This is still our axon at the top. Membrane's gone. Basically the entire membrane's gone, which is kind of funny. Which means two things. Number one, V membrane equals 0, voltage in the membrane equals 0. And it also means that the axon voltage is just equal to the battery. The axon has all the voltage. Any questions with that? Okay. So after a long time, the capacitor is an open circuit again. It's an open circuit again. This is still true from what I wrote earlier. What's different is it's not voltage equals Vmax and it's not current equals 0. Instead, the circuit looks like this. It's just two resistors. You just literally ignore the capacitor. It's still there, but it's just kind of invisible. So here's axon, here's membrane. Now, many of you out there think that the voltage in the capacitor is 0. And it's not because you're dumb. That's a very logical thing to think. There's no capacitor, so how can it have any voltage? Trust me, it has voltage. Again, there's a proof for it. I don't want to tell you the proof because it's just not worth it. You just need to know that voltage in the capacitor equals voltage in the membrane. Voltage in the capacitor equals voltage in the membrane, yes, from this resistor right here. In order to actually find that voltage, you need to use Ohm's law to find voltage. V equals I times R. We're going to do an example of this later on tonight, so if you're confused, don't worry, I cover it. Any questions? Okay. So then number 2, the resistance of a membrane is 4 kiloohms. What would be the new resistance if we doubled the thickness and cut the radius in half? A very famous problem because it is a comparison problem, which we saw in Physics 1, and we also saw on the first exam, right? So the way we solve comparison problems is I solve it twice. I solve it twice. Solve what twice? Well, in this question, it's asking about the resistance of the membrane. So let me write that equation again. This is probably given to you on the exam, so I don't think you have to memorize it. Personally, I would because I'm paranoid, and I don't like relying on his exam sheet because it never looks the way I expect it to look, so I always memorize it the way I do it. But anyways, this is, well, basically the solving it the first time, right? Like these are the original values. I know I don't know any of them, like I don't know rho, I don't know t, but it doesn't matter. They're all going to cancel out. Now, for R2, or R new, whatever you want to call it, what changed? We doubled the thickness and cut the radius in half. So if I double the thickness, that's now 2t. And if I cut the radius in half, is that going to be 1/2 the diameter or 1/4 the diameter? Who thinks they're brave enough to answer?
1/4 the diameter.
Thank you, Kyle. Or was that Spencer? Regardless, you're wrong. It was 1/2. Why? Because 2r equals d. And if you 1/2 2r, you're also 1/2ing d. The only time it's 1/4 is if there was a squared somewhere, like for instance here. Then it'd be 1/4. So let me erase that. And so now rho t is now 2t divided by pi 1/2 dl. Great, I now solved it twice. The first time was very easy, and the second time just change a couple variables around. Not bad at all. Then finally, the last step is you have to do R2 over R1. In other words, the new over the original. This is going to be a complex fraction, so I'll try and do my best to show this, but it's going to be rho 2t over pi 1/2 dl big fraction bar divided by rho t over pi dl. The next step is my favorite part. It's canceling out like literally everything. Rho cancels, t cancels, pi cancels. Yes, the d cancels even though it's in a parenthesis, and the l cancels. The only things that don't cancel are the 2 and the 1/2. That's it. And 2 divided by 1/2, you can plug that in a calculator. It's 4. Be careful though. The final answer is not 4. This is like the multiplication factor. In other words, if the original was 4 kiloohms, then you do 4 times 4 kiloohms. So your new resistance is 16 kiloohms. Final answer. Always answer the question. Be very careful. Any questions? Since Professor Young loves comparison problems, you are guaranteed to see a comparison problem. He calls it scaling factor or something else though. But it's at the end of the day, I call it comparison problems. It's the same thing. You solve it twice. Next we have number 3. I give you the radius of the axon is 75 ohms. Resistance. Resistance is 75. Resistance of the membrane is 150. Capacitance is 156. Battery is 6 volts. A lot of nice numbers there. What is the voltage on the capacitor and axon immediately after the switch is closed? What is the voltage across the... And then part 2, what is the voltage across the membrane and axon after a long period of time? So this is what I was saying earlier. We're going to do a short time and long time. I'm literally going to just repeat what I wrote earlier. So for short time, notice the battery is upside down in this circuit. That's okay. The point is the same. Axon is there. Membrane is gone. Axon is there. Membrane is gone for short time. So if I want the voltage on the capacitor will be 0 volts. You can just memorize that. The reason why is it's just a wire. Wires always have 0 volts. And so then if I want to find the voltage in the axon resistor, well, it's going to have all the voltage because, well, there's a battery and then one resistor. So that resistor gets all 6 volts. V axon equals 6 volts. Not bad at all. I know I didn't ask for current, but if I did, current I equals voltage, which is 6, divided by the resistance, which is just the 75 number. So it'd be 6 over 75. I didn't do that calculation earlier, but you know, it'd be 6 over 75. That'd be the current if I asked for it. Next we have long time. So again, for long time, I'm just going to use the same shortcut I talked about earlier. It's basically the circuit with just these 2 resistors, our axon and our membrane. The capacitor's not there, but remember, voltage in the capacitor equals the voltage on the membrane. It's not 0. Now, if I want to find that voltage, I got to use some Ohm's law. What that means is I'm probably going to combine these 2 resistors. So R total equals, I added the numbers up, 75 plus 150. They're in series, so it's not the weird 1 over math. And we get 225 ohms for total resistance. And then we got to find the current. I equals voltage total over resistance total. So that's 6 over 225. And that gets me current I equals 0.0267 amps. The reason why I need the current is because, remember, this circuit is in series. In other words, the current is the same everywhere. And now I'm going to use Ohm's law again to find the individual voltages. Like, for instance, here's the axon. Voltage axon equals the current, 0.0267, times resistance in the axon. That was the 75. If you plug this in a calculator, you'll get 2 volts. So that's the voltage on the axon. Any questions so far? Just one more step to go. That's going to be the voltage on the membrane. You can do current times resistance again, or even easier, you can do the total voltage 6 from the battery minus the voltage we just found in the axon. The remainder will be on the membrane, 4 volts for the membrane, and the capacitor by extension. Any questions on that one?
Could you just scroll back up to like your first part of the work really quick?
Right here.
Yeah, thank you.
Just let me know when you're done.
You're good. Thank
Okay.
you.
Yep, no problem. So that's it for the first section of the test with everything circuits related. Now, circuits are gone for good until maybe the final. I forget if it's cumulative or not. But regardless, we have something very fun, magnetic fields and magnetic forces. So these are similar to electric forces, obviously, and electric fields, except electric fields had to be parallel, meaning if I wanted an electric force, I needed an electric field in the same direction as my force. What we're going to discover with magnetic fields, it's the opposite. It needs to be perpendicular. I don't know why. To put this in an analogy for real life, it would be as if I'm walking north down the street, I feel a gust of wind coming from the east, and all of a sudden I start floating upwards. That's how much sense this stuff makes in real life. It doesn't, but it works out for electrons and charged particles, so that's nice. So first we have magnetic force. Magnetic force has 2 equations, depending on what I'm talking about. So the first one is absolute value, QVB sine theta. And the reason why I put the absolute value sign is because I figure out the direction by hand. And when I say by hand, I literally mean by hand with the right hand rule. Ha ha ha. This equation is specifically for a point charge, as opposed to a wire, which will be the next equation. This Q is charge. This V is velocity, not voltage. It is velocity. And B is the magnetic field, but I don't have room to write that. B is the magnetic field. Sine theta is always going to be 1. Technically, that's not true, but just take my word for it because it's 99% of the time, sine theta is 1. I'll tell you when the 1% when it's not 1. That'll come up later today. And then the second equation is Fm equals absolute value ILB sine theta. And as I stated earlier, this is if I have a wire. I is obviously current. B, again, is the magnetic field. The only one that you might not know is L. That is length. But if you want to write all 3, go ahead. And then we have the right-hand rule. So, fun fact, there are 4 different right-hand rules to use in this class. One for magnetic fields, one for magnetic force, one for Faraday's and Lenz's law, and one for the electromagnetic wave. 3 of those I just said will be on this test. The last one you might not cover at all. I'm not sure. We'll see. Okay, so for the right-hand rule for magnetic forces specifically, it's easy. First of all, there's 3 different ways you can do it. I will be teaching the way I call the handshake method. Okay, it looks like you're going to be doing a handshake. Other methods include the curl finger method, which works, but I only teach to people who well, no, I don't teach it to anyone that way. Unless they already know it, then I'll teach it. It's not a good way. It's very confusing. And then the other way is the physics gang sign method, which looks like I have a gun pointed at you, but with like a middle finger off to the side, which I call the physics gang sign method. Regardless, we're doing the handshake method, and here's how it works. Your thumb points in the direction of your velocity or current. Velocity if we're talking about the point charge. Current if we're talking about the wire. Then we have our fingers. Our fingers are going to point in the direction of the magnetic field. So just like you're making a handshake, thumb up, or at least thumb out, point your fingers out. That's the magnetic field. All 4 of your fingers, point them out. And then finally your palm, your open palm, that's going to point in the direction of the magnetic force. In my opinion, this is the best way to do this. If you disagree, that's fine. You're wrong. I've been teaching this for a long time. This is statistically the most effective way of doing it. But if you like one of the other methods, I'm not going to stop you. Okay. Note, very important note. If the charge is negative, reverse direction of force. Negative charges go the opposite way, as always. Any questions on any of that? We will be doing a ton of example with this right-hand rule and the other right-hand rule I'm about to say in another second. We're going to be doing that a lot today. Next, we have the magnetic field for a straight wire. There's technically a lot of magnetic field equations out there. Like, for instance, there's the solenoid, there's a curved wire, there's the toroid, I think it's called. But I'm only going to be talking about the straight wire one because that's the most common one. And if you do want the solenoid equation, let me know and I'll send you a video on that because I do have a video on it. So here's the equation. I think all these variables are straightforward. Well, maybe not mu naught. Mu naught is 4 pi times 10 to the minus 7. It's a constant. It will be given on the equation sheet, so don't worry. And r is not a radius, it's really just a distance. Then why do we call it r? Well, because it's based on the cylinder equation, which I'm not going to explain. Or maybe circumference of a circle. Yeah, actually circumference of a circle. If you really want to know, it involves a surface integral. If you want to know more about that, no, it's not surface integral, it's a contour integral. If you want to know about that, take Calc 3. If you don't want to know about that, good, don't ask questions. The fastest way to get ahead in life. Okay, next we have the right-hand rule. This is going to be just slightly different than the other right-hand rule. Our thumb is going to point in the direction of current, not velocity, because we're just talking about a wire with this one. Our fingers, once again, Well, this time the fingers are going to point from the wire to the point. What point? In the question, there will always be a point, like point P or point Q or point whatever, or maybe it's a point charge. Always point from the wire to the point. This is the thing that confuses most students. Please practice this. It's not that bad. And then finally, our open palm is going to point towards the magnetic field, which is usually the answer. One more thing to say about this. What this equation and what this right-hand rule is basically telling you that where magnetic fields come from, where do magnetic fields come from? Magnetic fields come from...
Current in a wire.
Thank you, Skylar.
Or a magnet.
Or a magnet. I'm not going to talk about the magnet. It's boring, but technically true. Magnetic fields come from current in a wire. A+ for Skylar. So what that means, if you look at a problem on this test and you say to yourself, there's no magnetic field, this is a trick question. Probably not. There's probably a current in a wire that's supplying the magnetic field. You have to use this equation to find it. Okay, so next we have number 4. What is the magnetic field at point P, both magnitude and direction? First we'll do the magnitude. You'll notice there's 2 wires here, a top wire and a bottom. We have to do them separately. Let's do the top first. So for the top, the equation is B equals mu naught I over 2 pi r. That's going to be 4 pi times 10 to the minus 7th times the current, 50 milliamps, or 50 divided by 1,000, divided by 2 pi r. 2 pi, and then what's the distance? Is it 28 millimeters or is it 56 millimeters? It's 28, just the distance to the point P. So that's going to be 28 divided by 1,000 because it's milli. You plug that in a calculator. 3.58 times 10 to the minus 7th. Units are Tesla, named after the car company, obviously, and not some famous physicist. Now, one more thing, since we're still on the top wire, we should find the direction. How can I find the direction? Oh, I use the right-hand rule, of course. So thumb points in the direction of the top wire. So in other words, don't write this down, just do it. Thumb points right. Your fingers are going to point from the wire to the point. Which direction is that? Down. Thank you. Thank you. And then finally, if your thumb points right, your fingers point down, then that means your palm should be pointing into the page, which is this symbol right there, into the page. Any questions on how I did that? Excellent. So now we're going to do the bottom wire, which is extremely similar to what we just did. Magnetic field B equals 4 pi times 10 to the minus 7th times, this time it's 75 over 1,000 for the current on the bottom, divided by 2 pi r, and it's the same distance, 28 over 1,000. Pretty straightforward. Plug this in a calculator, and I'll get 3.58 times 10 to the minus 7. But which way will this magnetic field point? Which way will this magnetic field point? My thumb's going left. My fingers point up because point P is above me now. And so that means my palm is still into the page. Because I got 2 into the pages. Wait a minute, that number's wrong. Sorry. 5.37. Sorry. Still 10 to the minus 7th. But anyways, it's still into the page. So if you get 2 into the page, then your final answer, you just add these 2 together. 3.58 times 10 to the minus 7 plus 5.37 times 10 to the minus 7. Final answer will be 8.95 times 10 to the minus 7, and that's into the page as the direction.
If one was like into the page and one was out of the page, would you subtract?
Yes, I would subtract them, and which one would be positive and which one would be negative. Generally speaking, I would just say the stronger one is positive. What do I mean the stronger one? The higher number. So like let's say this was into the page or the other one was out of the page. I would keep this guy positive and I would make this guy negative. But it depends on the problem because sometimes the question says choose out of the page to be positive, into the page to be negative. Do whatever the question tells you at the end of the day. But if you get to choose, the higher number should be positive.
Thank you.
Yep. Any other questions there? Okay. Next we have number 5. Number 5 has 4 right-hand rules for us to try. These are all right-hand rule for force. This is all magnetic force. So we're going to do them, well, kind of together. I'm basically going to say, like, for part A right now, try this on your own. I'll give you, like, 15 seconds, and then I'll tell you the answer. Okay, time's up. So my thumb is the velocity up and to the right. Fingers are going to point into the page. That's the end of the page symbol. My palm should be pointing up and to the left. So up and to the left. Does everyone see that? If not, then I guess you can email me later. Part B, velocity down, magnetic field up. Go ahead, give this one a try now. So this one's interesting because if you point your thumb down and your fingers up, it's kind of impossible. The reason why that's impossible is because this is sine of 180. It's 180 degrees up and down. Because of that, this is the 0 case. You will have 0 force whenever the lines are parallel. You need the lines to be perpendicular. If you can't tell if it's parallel or not, my guess would be it's probably perpendicular. Parallel is usually very easy to spot. Perpendicular is, like even the first one, part A, that's perpendicular. I know it doesn't look perpendicular, or at least you have a hard time visualizing it. I promise it will be perpendicular on the test. The only time it's parallel is when it's obviously parallel, like this one right here. Next we have C. Give that one a try. I want to give a hint. You'll notice there's no magnetic field, but I have a wire. That wire is producing the magnetic field. For this one, you need both right-hand rules. First to find the magnetic field, then to find the magnetic force. Okay, so for this one, first I'm doing the right-hand rule for this wire to find the magnetic field. So my thumb's pointing up. My point is the charge to the right. And then my fingers are pointing into the page. So that's going to be into the page. And I'm drawing magnetic field lines all over the place because it's into the page all over here. If you want to just draw one, that's fine too. You'll get the same answer. Now, for magnetic force right-hand rule, thumb points in direction of velocity now, because we're talking about the point charge. So velocity to the left, fingers magnetic field into the page, and then my palm is pointing down. So down is the wrong answer. This is a negative charge. You gotta flip it. It's up. Wasn't that clever? Any questions on that one? Okay. The last one we have here is part D. Once again, it's the same idea. This top wire here is going to be producing a magnetic field on this wire, and you're going to find the magnetic force on the bottom wire. So go ahead, give it a try. Okay, so for this one, thumb pointing to the left for the top wire. We're finding the magnetic field first. Thumb to the left. The point I'm looking at is below me. The wire is below me. And then my palm is pointing out of the page. So out of the page, all over here. Then I do the right-hand rule for the bottom wire for force. That's going to be thumb to the right for current, fingers pointing out of the page for magnetic field, palm is going to point down. Down is the correct answer. It takes some practice to get good at it. You can find a ton of problems online, or you can retry these later. But no questions? Okay. Next, we have magnetic flux, Faraday's law, and Lenz's law. Young calls this induction, which it technically is, but I don't hear anyone else call it induction. But that's what he calls it. So first, we need to talk about magnetic flux, because induction and Faraday's law comes from magnetic flux. The symbol is Greek letter phi, and that is going to equal B A cosine theta. B is magnetic field. A is area. The cosine theta is there. I'm just going to cross it out. It's more trouble than it's worth. I mean, if you want me to explain it, I will. Magnetic flux is at a maximum cosine value when the field line goes through it, like a bow and arrow through a hoop. And the flux is 0 when my arrow misses the hoop. It's like over it or under it. So this top picture is max flux, and the bottom picture is 0 flux. Any questions? So the next we have Faraday's law. Faraday's law, he calls E induced. He calls this the induced EMF. Sure, I call it induced voltage. EMF and voltage is the same thing. I think EMF is confusing, so I call it voltage. We all know what voltage is. The word induced means, and you don't have to write this down, but the word induced means this voltage is basically coming out of thin air. The induced voltage is technically coming from a change in flux, but here's the equation. Negative N, and I'll explain all the variables in a second, negative n delta flux over delta t. N is the number of loops. The number of loops. It is 1 by default. A lot of times you'll see me ignore that negative sign out in front because I want the magnitude. But as always, magnitude, you just make absolute value at the end. So that's easy. And one more thing you should know, or at least what I like to write. I need more room. I like to write it as E induced equals negative n BA final minus BA initial over time final minus time initial. Because I don't like delta notation. So I use final minus initial instead. Okay. So now, back to the third right-hand rule. And this is the final right-hand rule of tonight, thank God. This is going to be the curl finger method. So the way you do right-hand rule to figure out the direction of this figures out the direction of the current, by the way. I would say the direction of the voltage, but voltage doesn't really have a direction. Current has a direction, clockwise or counterclockwise. So here's how we do it. Step 1, and by the way, the first 2 steps do not use your hand, so it's only step 3 that uses your hand. Step 1, identify change in flux. The flux is either going to be getting bigger or smaller. It's your job to tell me which one. Step 2, create a magnetic field, a B field for short, to counter the change in flux. So step 2, create a B field in the opposite direction from step 1 to counter the change in flux. So as a very specific example, again, I don't recommend writing this down. If you find the flux increases going up, then that means the created B field goes down. The reason I'm telling you not to write that down is because you're just going to see some arrows on your page and you won't quite know what that means. But we'll see with some specific examples, that's going to be the real spot where it's going to help you out. Okay, so it looks like we're creating a B field. And I forget, maybe someone can help remind me, where do B fields come from? Skylar, that's your cue.
Current in a wire.
Yes, current in a wire. Thanks for not being a smart aleck and saying a magnet, because I don't have an answer for a magnet. But it's this B field is coming from a current in a wire. The right-hand rule finds the direction of this current. So your thumb is going to point in the direction of the created B field from step 2. Thumb is the created B field. So basically, if you get step 2 wrong, you're going to get step 3 wrong, basically. So don't make that mistake. And then this is the curl finger one. You're going to curl your fingers, and that is the direction of the induced current. And therefore also the induced voltage, but voltage doesn't really have direction. So induced current. Any questions? Okay. Number 6, this one's basically taken from his exam, but I made it, not his exam, his practice exam, but I made it a little bit different. A loop of wire with area 0.05 meters squared and 20 turns has a changing magnetic field passing through it. For the first 5 seconds, the magnetic field switches from 3 Tesla out of the page to 6 Tesla out of the page, and then for the last 9 seconds, the magnetic field switches from 6 Tesla out of the page to 3 Tesla into the page. Fill out the graph for the induced voltage in the loop. Consider counterclockwise and out of the page to be the positive direction. Okay, that's very helpful because it's telling us which way is positive, and they should do that on the test. So the way I would approach this, first I just want to write down the information I know. Like for instance, area is 0.05 meters squared. I know number of turns is 20. I know for the first 5 seconds, we're switching 3 Tesla out of the page to 6 Tesla out of the page. And then for the last 9 seconds, we're going to be going 6 Tesla out of the page. And then we're going to 3 Tesla into the page. Be careful there. So basically, I'm going to have different graphs for the left side and the right side of 5 seconds. Okay, so basically I'm going to use the equation. The equation is E induced equals negative n BA final minus BA initial over time final minus time initial. Makes sense. So n is 20. B, I'm looking at the first 5 seconds. B final is 6 out of the page. Is out of the page positive or negative? Let's see. Out of the page is positive because it says it in the question. Great. So 6 times area, 0.05, minus B initial. Initial is 3 out of the page, so positive 3. Well, minus positive 3. Times area, which again is 0.05. And then divided by the time. This time is 5 seconds. So you plug this in a calculator, and we'll just get negative 0.6 volts. Now, I have a decision to make. It's either going to be, here's 5 seconds, there's negative 0.6. So it's either going to be a linear line like this, or it's going to be a constant line like this. Any brave souls want to take a guess? The answer is the red. How come? Because I said so. And it will always be a flat line. If you want the actual reason, the reason why is because this voltage is representing a rate of change, and the rate of change is constant. And we know from Calculus 1 that the rate of change is constant. It's going to be a flat line on the derivative graph. So like I said, it will always be flat. Don't ask questions. Then for the last 9 seconds, this is conveniently 5 to 14. That's 9 seconds. Would you look at that? I'm literally just doing the equation again with new numbers. So for this one, it's negative 20. This time the final is negative 3. And I say negative because it's into the page. Into the page is negative. So negative 3 times 0.05 minus the initial. And by the way, this is the initial, like, the end of the 5 seconds is the beginning of the 9 seconds. In other words, I'm talking about the 6 Tesla out of the page. And that's times 0.05. Divided by time, which is 9. You plug this in a calculator. Positive 1 volt. So then back here, I know it's going to be positive 1, which is going to look like this. So I guess the question is, what am I going to do at 5 seconds? And the answer is, just draw a vertical line like that. That's fine. That's fine. That's what I would do. Any questions on that one? Okay, good. That's a tough one, by the way. But it's a good problem. Next, number 7. This is a very, very famous example with Faraday's law. A bar is sliding to the right at a speed of 2 meters per second as shown below. A magnetic field points out of the page with strength 250 millitesla. What would be the magnitude and direction of the induced current? So they're not asking about voltage, they're asking about current. That means I gotta first find the induced voltage, and then I gotta use V equals I times R, Ohm's law. So that's the strategy. Now when it comes to the sliding bar example, there is a proof. Obviously I give us this whole page to write the proof, but I decided at the last minute I don't want to write the proof because I wouldn't write the proof on the test. So let me just give you the equation. Epsilon induced, this is specifically for the sliding bar example, epsilon induced equals NBLV, or I guess negative NBLV, but we just never see the negative sign. It's always going to ask for the magnitude in the sliding bar example. It just does. Now, here's the $1 million question. Well, actually, first, real quick, that V is velocity. It is not voltage. I know V is also voltage in this class. I didn't get to choose that. I would have chose something different. But at least I try and use lowercase v for velocity and capital V for voltage. Now, the question that's burning you right now is this L right here. I gave 2 lengths, 4.5 and 3 meters. So which one's the right one to use? I'll tell you. It's the 3. It's always the constant. It's the constant length. What do I mean the constant length? Isn't the 4.5 dimension getting longer? Like as I move this bar to the right, isn't that dimension getting longer? But the 3 meters is staying the same? So always choose the one that stays the same. So in this example, very easy. I don't think it says any turns, any loops. So n is 1. It asked for magnitude, so I'm taking absolute value, no negative. B is 250 millitesla. That's 0.250 Tesla. 0.25. L, like I said, is 3. And the velocity is 2. They say it in the problem. So this question seems very easy. The answer is just going to be 1.5 volts. Do not circle that answer. That's the voltage or induced EMF. Same thing. If you want the current equals voltage divided by resistance. So that's going to be 1.5 divided by, it said the resistance was 150 ohms. Plug that in a calculator. 0.01 amps. Any questions? We still have to find direction. I didn't forget. So now for the direction, I have to do the right hand rule. This is fun. So first, my thumb is well, actually, I jumped the gun. Step 1, what is the change in flux? As the bar moves to the right, my flux is increasing, because if you're going to the right, then that means you're getting more and more flux. You're getting a bigger area here as I move to the right, so more flux. So we know flux is increasing. Okay, then how am I going to counter that flux? The answer is you create a magnetic field going into the page. This is going to counter it. Technically, I only need to draw one of these little symbols, but I'm going to draw a bunch just to show the idea. So created B field is pointing into the page. And then finally, right hand rule. Thumb points in the direction of the created B field into the page. Then I curl my fingers, and if you're curling your fingers correctly, you're getting this kind of clockwise motion, and that's what the answer is. Clockwise current. Any questions? I know it's hard. We'll be doing a few more examples of right hand rule in the next problem. One more side note to mention. This I would call an extra credit question. Fun fact, I obviously tutor more than just you guys. Most recently, I'm tutoring some kid from, I don't even know what high school they go to. Maybe Texas or something like that. Anyways, she sent me a question that looked just like this, but you know, it was multiple parts. Part 1 and part 2 was just finding voltage and current. Here's where it gets really interesting. I never thought of this before, so it blew my mind. The question, as you know, the current flows like this, okay? Obviously, we just said that clockwise. Okay, fine. That means you have a current pointing down, right? And if you have a current pointing down, then that means, oh, and that blue thing, that blue arrow, is inside of a magnetic field. What I'm trying to get at is there is a force acting on that bar. You never have to consider it unless the question asks for it. I've never seen Young or any college professor ask this question before, so don't expect to see this, but it's a fun question to think about. If that current points down, current down, field out of the page, palm points left. As you pull it to the right, you feel a little bit of a resistance force pulling it to the left. That's going to be the magnetic force pointing to the left that's resisting you trying to do this motion. Coincidentally, if you go the other way, you feel another resistance force pointing the other way. So I just think it's very interesting. If you think it's confusing, then you're right, it is confusing. So I'm just going to move on. For number 8, we have a bunch of right hand rules. The question is, state whether the current will point clockwise, counterclockwise, or 0 for the following examples. So once again, I'm going to give you like 15 seconds per problem. So go ahead, try part A. Okay, time's up. So for this one, I noticed that the flux is increasing. The flux is increasing out of the page, which means my created B field points into the page. That's the created one. Thumb points into the page, curl my fingers. That's going to be clockwise for that first one. Now part B. Time's up. This one's kind of the opposite. This one is increasing into the page. So my created magnetic field needs to point out of the page to undo that. And so therefore my thumb points out of the page, curl my fingers. That's going to be counterclockwise for that one. Any questions? Okay, C. Okay, time's up. This one is getting weaker into the page. So the opposite of weaker into the page is stronger into the page. My created B field points into the page to make it stronger. So, into the page is the thumb. Curl my fingers. That is going to be clockwise again. And then finally, part D. So this one's definitely the toughest one. So first of all, I want to say the answer is not 0. The reason why is flux is equal to not just the magnetic field. The magnetic field is actually staying the same here, as evident by there's just one circle in both. But what's increasing is the area. And so I have increasing flux, and it is increasing out of the page. If that was into the page, then obviously it'd be increasing into the page. So when you increase the area, you're increasing it in whatever direction it's already pointing. But the magnetic field itself is staying the same. So if I'm increasing out of the page, then my created B field, of course, needs to point into the page. So if my thumb points into the page, curl my fingers, this one's clockwise too. Any questions on any of those? Okay, great. Just a few more problems to go. Next, we're on Snell's law, and this is eventually going to lead into lenses. So Snell's law is talking about the refraction of light. What does that mean? Great question. Refraction is talking about the bending of light. When you have light, light can do 3 things. It can reflect, which we know what reflections are. It can reflect, it can refract, which is bend, or it can, oh, what's the third word? It doesn't matter because it's on the final, not on this test. Oh, what's it called? Diffract. That's what it's called. Diffraction of light. That will be on the final with Young's double slit experiment, which is funny because I believe all of you know this. Young, first of all, his last name's Young. And so what he did in Physics 1, he put Young's modulus on Physics 1, which was never covered before in Physics 201, before Young did that. And now we're going to talk about Young's double slit experiment, which in his defense, this actually is covered by every Physics 2 class in the country, basically. But it's just funny. Coincidence. So anyways, here's the equation for Snell's law. N1 sine theta 1 equals N2 sine theta 2. And yes, I'll answer your question now. What's N? Great question. N is the index of refraction. Now I know what you're thinking. That's not very helpful. I know. So here's the important part. The higher the N, the slower light moves. So higher actually means slower. Interesting. If you didn't know that, yes, light does not always move at the speed of light. Light only moves at the speed of light in a vacuum, like outer space. Air is pretty close. It's like 1.001, so it's like very close to 1, which is the smallest value. So anyways, here's the idea with Snell's law, with the equation specifically. As N goes up, theta goes down. As N goes up, theta goes down. So as an example, let's say hypothetically I have this, and here's N1 and here's N2, right? And here's theta 1. And then let's say I draw a line, and the line on the other side of this index, whether it's glass or water or whatever, let's say the reflected line looks like that, and now here's theta 2. Always measure from the perpendicular line. Always measure from the perpendicular line. Now the question for you is, which N is bigger, N1 or N2? Well, bigger angle, smaller n. Theta 2 is bigger, which means n1 greater than n2 for this one. And if I had a line going the other way, more towards the vertical, it would be reversed, obviously. Now, one thing you need to know, there is something called complete reflection. This occurs at the critical angle, which is maybe a bit dramatic, calling it the critical angle, but whatever. You get complete reflection first if n1 is greater than n2. This does not happen for the other way around. You need to be going to a lower n value. And then it's when theta 2 is greater than or equal to 90 degrees, or, and this is the funny answer, or if your calculator gives you an error. It's when theta 2 is greater than or equal to 90 degrees, or if your calculator gives you an error. You'll know it when you see it because your calculator will literally say error. If this ever happens, it means you get complete reflection. To show us on this picture I started drawing right here, it would look like this red line right here. That would be complete reflection. And these thetas match perfectly. Theta 1 and theta 1 match perfectly. Because it's like a mirror. Any questions on any of that? Okay. Number 9. Light passes from air, n equals 1, to glass, n equals 1.4, and then back to air. The angle of incidence between the air and the glass is 45 degrees. Finish drawing the refraction lines below, and then find the angle of incidence with the glass. So first, here's n1, which is 1, n2, which is 1.4, and maybe we have n3, which is okay. n3 is 1 again. So basically what I notice with this picture is first, I'm going to a higher index of refraction, and then I'm going to a lower index of refraction. And so what that means is if first I'm going to higher, the angle is going to be smaller. It's going to look like this. This little sliver right there, that's theta. I guess theta 2. And then when we hit the glass air interface again, it's going to bend outward more because again we're going to a lower. Now will the first line and this third line be parallel? This line and this line I'm talking about? Yes, they will be parallel. If this is 45 degrees, then that means this down here is going to be 45 degrees. Don't believe me? Do the math, it will work out. Now the question is still asking about theta 2. So we got to find theta 2. Luckily, it's easy. I'm literally just using Snell's law. n1 sine theta 1 equals n2 sine theta 2. So n1 is air, we're saying, 1 times sine of 45 degrees equals n2, which is 1.4, and I ran out of room, so let me write it over here. Sine theta 2. I think it's pretty obvious that we divide by 1.4. If you plug the entire left side in a calculator, you'll get 0.505 equals sine theta 2. And then hopefully you know how to do this. If you don't, to solve for theta 2, you take the inverse sine of your answer, and that'll get us the final answer of theta 2 equals 30.3 degrees, which, remember, is smaller than the original 45 degrees, which makes sense. Any questions? Great. Now, number 10. Is it possible to have complete reflection in the example below? If so, state the minimum angle needed to have complete reflection. In other words, the critical angle. Well, let's think about this. We have n1 here, n2 here. Looks like I'm going to a lower index of refraction, which means yes, it's possible. Well, then how do I find it? So here's how you find the critical angle for complete reflection. n1 sine theta 1 equals n2 sine 90. This is always the equation specifically for the critical angle. And now we just plug in. So n1 is 2.7 sine of theta 1. You're solving for theta 1. We don't know theta 1. Equals 2.2, and then the sine of 90 is just 1. So then divide both sides by 2.7. So sine theta 1 equals 0.8148. And then we take the inverse sine again, and that's going to give us a final answer of 54.6 degrees. So any farther than 54.6, and we are going to have complete reflection. And that this idea is basically the same reason why, it's not exactly the same reason why, but sometimes when you look in the water, like a pond, you can see your reflection. It's a similar idea to that. Any questions? Okay. Now for the second to last topic of tonight, which is lenses, which is not the same thing as Lenz's law, because Lenz's law is with Faraday's law, but whatever. So one quick side note, once again, I like to talk about side notes. When it comes to lenses, you guys have it easy because a lot of students in the past with Physics 202 at Delaware, they learn mirrors before lenses. That is a nightmare. I hope you never have to do that. I don't think you will ever do that. But the reason why that's so bad is because mirrors are just like lenses in every way, except it's just slightly opposite. If it was completely opposite, it would be very easy for me to teach. But it's slightly opposite. And what does that mean? It means it sucks to teach and it sucks for my kids to learn, so we all just have a bad time. So the good news is you just learn lenses, and then you don't have to get confused halfway through. So anyways, here's all of the equations. I'm going to use the notation that Professor Young uses, even though I personally don't like it at all. The equation is 1 over f equals 1 over s plus 1 over s prime. F is the focal length. If you want a definition of focal length, this is where all of the light converges in a lens. I'm not writing that down because I don't have enough space to write that down. But it's where all the light converges in a lens. S is going to be the object distance. In other words, how far away is your object from the lens? And then we call S prime the image distance. Obviously, the distance from the image to the lens. You should know that S prime can be positive or negative. I'll explain more on that later. But S is always positive. The object distance should always be positive. Unless you're talking about a compound lens in a very specific instance with the compound lens, which I'm not going to get into because I mess it up half the time and I don't feel confident with that right now. So just ignore me babbling. Then we have magnification. The equation for magnification is capital M equals negative S prime over S, or height image over height object. I guess I should use the same notation he uses then, right? H prime over H, where H is height. Okay, now here's everything you need to know about real images. Real images, first of all, the S prime is greater than 0. It's positive. Real images will always be inverted. Unless you're talking about compound lenses, then again, it's too confusing. And it's always going to be on the opposite side of the lens. This is all true for real images. You may have heard real images can be projected onto a screen. Is that true? Yes, but it doesn't help you on the test, so why write it down? And then we have virtual images. Virtual images are where S prime is less than 0. It's negative. These images will always be upright. And these are going to be on the same side as the lens. Any questions so far? Okay. Finally, we have the converging lens versus the diverging lens. Here's what you need to know. For the converging lens, for the math, everything I'm about to say is for the math, f is greater than 0. It has a positive focal length. What does that mean? Who cares? It's a positive number. That's all you need to know. I'm sorry I'm so combative with this topic. It's just there's a lot of information and it's very easy to get overwhelmed, and I don't want to overwhelm you. So if you have any extra questions after this, please stick around. I'll be happy to answer anyone's question, or you can email me afterwards. I'll answer your emails too. So then here's what a converging lens looks like. Looks like a little oval, and we put a dashed line in the center as the center of the lens. That matters for the ray diagrams, which I'll be covering on the next page. And what you need to know about the converging lens is that it can create any image except virtual and smaller. So in other words, we can make real and larger, real and smaller, and virtual and larger, but we can't make virtual and smaller. That's going to be the diverging lens. Then we have for diverging lens, this is when f is less than 0. The diverging lens looks like this. And then I write can only create virtual and smaller. Any questions? So, we have a couple questions with lenses. The focal length of a converging lens is 40 centimeters. I'm going to write this down as I go. F equals 40 centimeters. This is not me reading the question. The nice thing about this whole topic. It's one of the only topics in physics I can just leave everything in centimeters units because the units cancel at the end. The only exception to that, when we get to myopia and hyperopia at the end of this review, I have to use meters. But for right now, I can still use centimeters. F is 40 centimeters. The object is placed 65 centimeters away from the lens. So S equals 65. Find the image distance from the lens. Will the image be real or virtual? Will the image be larger or smaller? Okay, so this is very straightforward. I'm just going to plug in my equation. 1 over F equals 1 over S plus 1 over S prime. So that's going to be 1 over 40 equals 1 over 65 plus 1 over S prime. First thing I'm going to do is subtract 1 over 65 from both sides. That'll get me 0.00962 on the left. On the right, I'm still left with 1 over S prime. And then if you want to solve for S prime, you invert it, flip it. It's going to be 1 over 0.00962 or 104 centimeters. And there's my image distance. Now we have some questions to answer. Will the image be real or virtual? And will the image be larger or smaller? Any takers?
I think it's a real image. It's going to be inverted and it'll be smaller.
And why do you think that?
Because S prime is greater than 0.
Slow down. S prime greater than 0. So you're saying it's real, and I agree with that. Continue.
Wait, now I forget why I thought it was inverted.
Inverted's correct because real images are always inverted.
Okay, and then if you do the calculation for the magnification, it's negative, so it'll be smaller.
Okay, wrong. Negative magnification means inverted.
Oh, okay.
Basically, S prime is greater than S. In other words, 104 is greater than 65. That means we are larger. In other words, if I was smaller than 65, it would be smaller. And here's one of the, to go along with this, here's one of the most confusing things about lenses. Farther equals larger, not smaller. I know in real life, if something's farther away, it looks smaller. I agree with you. I'm not questioning that. But as far as lenses are concerned, if you get a farther image, it is going to be larger. And vice versa. Closer is always smaller for lenses. You'll be able to see why when we do the ray diagrams on the next page. Okay, next, number 12. Number 12 is a hard one, but I'm going to make it seem easy, so don't be fooled. This is a hard one. When an object is placed 8 centimeters in front of a converging lens, we notice the image produced is virtual and larger than the object. We then repeat the experiment after doubling the distance of the object from the lens, and we notice that the image produced is now real and larger than the object. Give a range of possible values for the focal length. Okay. So here's what I'm going to say. We can kind of split this up into 2 parts. If you try and start this problem by saying 1 over f, don't write this down. If you start the problem by saying this, you're not going to get very far. I have S, fantastic. I don't have F and I don't have S prime. This is just not a good way of doing it. So then what should I do? I'll tell you. First, I would start with the fact that this image for the first one is virtual and smaller. I'm sorry, larger. Virtual and larger. Since it is virtual and larger, and I say it's a converging lens in the problem, I already know f is greater than 0. If it was diverging, it would be less than 0. So virtual and larger, this is something I'd recommend memorizing because there's no way this is on the equation sheet and it's very hard to derive this. But if you have virtual and larger, you need to know f is greater than s. In other words, s is very small. You are inside the focal length. If the focal length is, for instance, 20, then s is smaller than 20. So I know f is greater than s. And that's really all I know for the virtual and larger. Now for the real and larger. For real and larger, the only way you get this, again, I recommend memorizing this, the only way you get this is if f less than s less than 2f. You need to be in between f and 2f. Where did 2f come from? I don't know either. That's why I say memorize this. If you're wondering what all the ranges do, I'll tell you in a minute. But first with this problem, notice that the real and larger, I had to double the object distance. So in other words, this is really 2s, right? And so now watch what I'm going to do. I'm going to plug in s. So for this first scenario, f is greater than, s was 8 centimeters. So great, I know f is greater than 8. And then for the second scenario, f less than 2 times 8, 16, less than 2f. Maybe you forget this from your math days, but what you should do is write this as two different inequalities. F is less than 16 and 16 less than 2f. F less than 16 is already solved. And to solve for the other one, just divide by 2. And I'll get f, I'm flipping the order, f is greater than 8. Or you can say 8 is less than f, same thing. So now I have 3 things to worry about. F greater than 8, f less than 16, and then f greater than 8 again. Okay, great. I have a repeat, so it doesn't matter. But basically what we know is that f has to be greater than 8 and less than 16. So if they want a range of values, fantastic. My range is 8 less than f less than 16 centimeters. And there's where my focal length can lie, between 8 and 16. Like I said, I'm going to make this seem simpler than it is. This is not easy to do on your own. I know. But there's a question similar to this on the exam review I saw. So maybe this will help you answer that one. Now, as promised, I said what the different ranges would do. Here's all of the ranges for converging lens. I'm not going to give diverging because it's literally all the same. It doesn't matter, virtual and smaller. So if S is less than F, this is virtual and larger. My object is closer than F. If S equals F, this one's funny, you get no image. Literally just no image forms. There ends up being a 0 in the denominator, and as we know, that's undefined. Then we can have F less than S less than 2F. This is the real and larger case we said a minute ago. And again, 2F is basically coming out of nowhere. I don't know why, but it is. Then we have S equals 2F. This is real and same size. And then last, S is greater than 2F. this is going to be real and smaller. And there you go. That's all 5 ranges for converging lenses. Any questions? Okay. Next thing to do, just a couple things left and we're done. Next thing we're going to do is the ray diagrams. Now, I don't know if this will be on the test or not. Maybe they'll draw them. Maybe you'll have to draw them. I don't know. But I'm pretty sure they'll show up in some way, shape, or form. So I want to be ready for them. So here's what I'm going to do. I'm going to teach you how to draw them. The good news is that since I'm recording this as a video, you'll be able to go back and exactly see what I'm doing in real time. Because these images are going to look really messy, but watching the video is going to make it really nice. So all the rules I'm about to say are specifically for a converging lens. I'll explain what to do for the diverging lens. Don't worry. So step 1, let me just write this over here. It's about to be a mess. Step 1, you're going to draw a straight line, then bend through the right focal length F. Maybe you didn't know this. All lenses have 2 focal lengths, one on the left side, one on the right side. You are going to draw a straight line. It's going to hit the lens, and then you're going to bend it through the right focal length F. And then you just draw one more line. The second line, go through left F focal length, then go straight. And we'll be doing this a bunch in a minute or so. 2 more things to note. As promised, for the diverging lens, switch left and right F. Just switch, the rules. Straight, then bend through left F, go through right F, then go straight. Again, we'll be doing practice with that. And lastly, this is more of a tip. This is kind of optional, but if it's a virtual image, and we know what virtual image means, it means quite a few things. It means it's upright. It means it's going to be on the same side of the lens, right? So whenever we have a virtual image, draw dotted lines on same side of lens. And again, I'll be showing you what I mean by this because it can get confusing. Okay. Great. Here we go, ray diagrams. First line, as I said before, it goes straight and then bends through F. So straight and then bend through F. When I say bend, I just mean, go that way. Don't make it curvy, make it straight lines. Then the second line goes through the left F and then it goes straight. And where these lines meet, that's where the image is going to form. So as we can see in this case, this image is real because it's on the opposite side of the lens. It's inverted because all real images are inverted. And this one, I don't know, I guess it's like a little bit larger. I'll write larger in parentheses, but it's kind of hard to tell. Any questions? So hopefully that made sense. If not, the second one's really not going to make sense. So here we go. Again, we have a converging lens. So I follow the normal rule. Straight and then bend through F. Okay, the second line's going to be confusing because the second line says to bend through the left F, but then we're never going to hit the lens, right? So here's what you do. You go through F, and then you turn around, and you hit that lens anyway. You turn around. And then you bend straight. But there's a problem. These lines will never intersect. Correct. That's what makes this a virtual image. So like I said with virtual images, you go backwards. Well, I don't know if I actually said that, but you go backwards. So watch how I go backwards. First of all, dotted lines representing the virtual image. And I'm going backwards like a mirror image from the right side. Mirror image from the right side. So there's where my lines intersect. There we go. And we say this image is virtual, obviously. It is upright. Again, we can see that. And this one's going to be definitely larger. Any questions? Okay. Then the last one, the diverging lens. Watch how I do this, okay? I go straight, and then I bend through the left F. I have to switch. Notice because I'm on the same side, I went to a dotted line. I did that intentionally. Then for the second line is going to bend through F like that. But notice right here, I hit the lens, right? So as soon as I hit the lens, I'm supposed to go straight. But obviously I don't intersect, so I actually go straight the backwards direction. And right there, where my two dotted lines intersect, the dotted lines, that is where the image is formed. As I can see, it's virtual, upright, and definitely smaller. Any questions? Okay. Then finally, the last topic of tonight, we're almost done. Just this one problem. Well, first the notes on this stuff, and then one more problem, and then we're done. Okay. So, if someone is myopic, then that means they are nearsighted. And I know this sounds obvious, but I'm writing this anyway. It means they can't see far away. Now, myopic people, they have something called a far point. The far point is the farthest point they can see. And we say the far point is smaller. In other words, closer than normal. The far point is smaller or closer than normal. And then the last thing, this is going to requires a lens with negative refractive power. And that's going to be a diverging lens. Requires a lens with negative refractive power And it's going to be a diverging lens. So one thing to note, we're going to be talking about how we measure the power of lenses and stuff. Power is going to be measured in something called diopters, which is a very funny name. Diopters. Which has the equation D equals 1 over F, 1 over the focal length. And this needs to be in meters. Needs to be in meters. Just to be clear, F needs to be in meters. The units for diopters are D, capital D for the units. Now we have hyperopic people, which I don't have enough room. These people are going to be far-sighted. Again, I know this is obvious. I'm sorry. These people cannot see close. We say that their near point is larger, aka farther than normal. And lastly, they're going to requires a lens with positive refractive power, which is a converging lens. Any questions? Okay. So then last question of the night. A patient goes to the optometrist for a new pair of contacts. Without any corrected vision, she can only see up to 80 centimeters away. What power contact lenses should the optometrist prescribe? Okay. So basically the idea with this problem is that we're using the equation 1 over F equals 1 over S plus 1 over S prime. We always use this equation. Now, here's the thing with how these problems go. So just take this with a grain of salt. If she can see only up to 80 centimeters away, I am not saying the object is 80 centimeters away. I'm saying the image is 80 centimeters away. The way glasses work, they take an image that's, let's say, farther than 80. Let's just say it's 160 centimeters away. The glasses project an image as if it were 80 centimeters away so that you can see it. Pretty cool. But the question is, how far is the distance S if I don't give a distance? The answer is infinity. In other words, infinitely far away. Infinitely far away. So basically the idea is, if these are good enough contacts, then you should be able to see clearly up to an infinite distance away. Now, just to be clear, I have 20/20 vision. I cannot see infinitely far away, but I'll tell you, no matter how far away the thing is, it doesn't look blurry to me. And that's the idea. That's the idea. Now, again, fun fact, because it's fun to talk about real life. My wife, which, yes, I get to say the W word now, because in January I got married, but that's neither here nor there. My wife has terrible vision, extremely bad myopia. She has diverging contact lenses and even diverging glasses, not at the same time, obviously. But she can only see, even with her glasses, she can't even see that far away, which is ironic. The reason why is because the way, the optometrist works, you're not trying to see infinitely far away. The glasses are kind of designed for a far point of about 10 to 20 meters. Having said that, choose infinity for this problem, even though it's not real life. So, anyways, 1 over f equals 1 over infinity plus 1 over, careful, 0.80. Remember what I said earlier. These are the only problems you have to convert to meters. Fun fact, 1 over infinity is 0. I know you don't have an infinity button on your calculator, but just trust me. So that means 1 over f equals 1 over 0.80. And here's a nice trick for you. I don't have to solve for f. Remember, diopters equals 1 over f. In other words, equals 1 over 0.80. So I'm like good to go. 1 divided by 0.80, which, by the way, I guess I'll say the punchline in a second. This gets me 1.25 diopters, and that, of course, is the wrong answer. Can anyone tell me why? I know you want to go home and go to bed, but I do too.
Should it be negative?
Why?
Because she's nearsighted.
It is nearsighted, yes. So nearsighted should always be negative. But that's not a good answer, you know what I mean? Like, there should be a mathematical reason why. And there is a mathematical reason why. This image that is being projected with the glasses, last time I checked, we want our glasses to not make images that are upside down. So glasses are always, and contacts, are always going to make virtual images. And so for that reason, it was actually negative 0.80, negative 0.80, negative. So yes, negative 1.25. That's why it's negative. But if you just remember that myopia should always be negative, then you're good too. Any questions on that one? Okay. Well, that does it for this exam review. Best of luck for your exam next week. And of course, if you have any questions, just shoot me an email and I'll get back to you. Have a good night, and I'll see you later. Bye-bye.
Thank you so much.
You're welcome.
Bye, thank you.
Bye.